Okay, so today we're looking at classification of matter. This is back to Chem 1. Good news is I'm not going to give you a lot of crazy examples of real life stuff like Rocky Road ice cream and pond water and all those things that sometimes could be one or the other when you're trying to classify. I'm going to only give you good chemical examples, and we're going to use those in tests and quizzes. So matter. All matter can be split up into two types of things: mixtures and pure substances. All right? Pure substances basically are anything that comes from the periodic table. You have elements by themselves, or you have compounds which are composed of elements. These are of a definite composition, and they can't be separated by physical means. Okay? So you guys just provided me with a list, which I turned the recording off for because they don't need to, at home, need to hear all our examples of all the different types of pure substances. When you get into the world of mixtures, there are two kinds of mixtures. There are heterogeneous mixtures and homogeneous mixtures. Can anyone remember the difference between heterogeneous and homogeneous, or homogeneous, some people say? You can see different things. What do you mean by things? Yeah, mixtures in general can be separated. All mixtures can be separated by physical means. Unlike these things over here are hard to separate. But I can argue that I can separate either. But Michael said that he could see different things. I want to know what that means. Becca? Morgan, you're Becca. God, because she have two blondes together. That was my thought. Parts, phases. I was looking for phases. There's obvious phases in a heterogeneous mixture. Grant? Yeah, you can see different aspects in it. A way I like to think about it, if I had 2 cups of the mixture, if I were to take a spoon in one and a spoon in the other, they'd look the same. There's no distinct differences. It's uniform throughout. Okay? Does that make sense? Can someone give me an example of a heterogeneous mixture? Now, I don't want you to think these are all liquids, and that's an important aspect. We can have mixtures that are all gases. We can even have mixtures that are solids, like Miles. Miles yelled out bronze before when we were talking about pure substances. What's the deal with bronze? It's a melted mixture of metals. There's another name for that, an alloy. So all our alloys are mixtures. My question is, which mixture would an alloy be? Homogeneous, yeah. Totally uniform throughout. Oh, why did I write homogeneous under homogeneous? Things like bronze. I have a carbon bike now, but in the day I had a titanium aluminum mixture bike, or was that my golf clubs? I can't remember. My bike was aluminum with something. I thought it would be titanium. That would be awfully heavy. So anyway, you have bikes, golf clubs, all that stuff made out of these alloys. Got it? What are some other homogeneous mixtures? Salt water. What else? Air. Beautiful. There is another name for a homogeneous mixture that's common. Air, bronze are all what? Who remembers? Starts with an S. Solutions. Solutions. All right. Give me some examples of some heterogeneous things. I can't hear. Trail mix. We're going to go to the food here. I feel food coming. Miles, what? Pond water, yeah. A mixed salad. Y'all are making me hungry. Okay. Sand and water. If I put oil and water together, right? Any nonpolar substance, you know that density problem we did yesterday with the layers? That would be a heterogeneous mixture. Okay, so these are pretty clear, and you're not going to get any crazy examples like people will argue air is not always a mixture if there's dust flying around in it. That kind of, I mean, homogeneous if there's dust flying around. Yeah, that's true. All the examples you're going to get are going to be very straightforward, simple. You shouldn't have any trouble on your homework tonight, okay? Now, this is really important. You get the demo cough. That means it's on the test when you hear me do that. What's new this year on the AP exam is the need to draw particulate diagrams or to interpret particulate diagrams. So you're going to see a lot of me making you draw stuff, and you're like, are you kidding me? I have to draw this? And I'm going to be like, yes, you have to draw this. You did a few drawings on day one. Okay, kind of weird drawing balls on paper, but that's going to happen a lot. So I'm not going to sit here and make you draw it right now, but I want you to keep it in mind, and I want you to practice when you can. And you're going to have to be able to draw things like single atoms and how they change to make compounds. You're going to need to know what the difference is between drawing a diatomic versus a compound. How is this diatomic drawn differently than that compound? You've got two of the same sized ball attached to another one just like it, okay? Versus that water molecule that has different elements attached. You're going to have to know how to mix these guys up together. If I say to draw a mixture, you're going to have to be able to draw a mixture, okay? Those kinds of things. You might have to draw reactions. You might have to draw compounds being decomposed to elements or vice versa. You might have to indicate state of matter visually. So here we have steam. Why does that look like steam? I mean, we got these little shoom at the end coming off, showing they're moving very quickly. What else makes this seem to be steam? Scattered and far apart. Okay, gases are further apart than liquids. Liquids are closer together. Now, this right here, water, in its drawing is a little bit of an exception. You see how liquid water, it looks like it's kind of flowy, that kind of thing? Yeah? Well, here we have solid water. Water is an exception because normally when something goes from liquid to solid, the molecules get closer and closer together. So they get denser and denser and denser, making the solid heavier than the liquid. So if I were to melt iron and have liquid iron in a vessel and drop a piece of metal iron in it, what's going to happen to that metal iron? Bam, it's going to sink to the bottom. Because it's heavier, it's more dense, and those molecules are visually closer together. This is important about water. Look at water. Are these molecules in the solid closer together or further apart? They're further apart. So this is actually less dense than water liquid. That's why, what does ice do? Floats. It floats, okay? The question I have for you, and we're going to get into an entire unit on this, why does water do this? Water's the only thing that does this. Remember the butt diagrams, how you had the negative or positive slope on the line? This is what all of this is about. Christopher, are you going to say something? Were you going to say something? Somebody, I heard a voice over here. Does anyone remember? It has to do with a particular intermolecular force. Not buoyancy. Polar molecules have possible different intermolecular forces, but water specifically has a type of intermolecular force that causes this to happen. This means I have to pause the video because y'all are taking so long. So I heard it's the hydrogen thing. Yeah, that hydrogen thing called hydrogen bonding. Hydrogen bonding isn't a literal bond. It's an electrostatic attraction that exists between some polar molecules, not all of them, specifically in water. And so water has to align this way in solid form to get to have the most interaction, to be most in connection with other water molecules around it. So our red side, red is the oxygen, that's partially negatively charged because of all the hydrogen bonding. It's then going to be attracted to the hydrogens in the neighboring and vice versa, and you're going to get this network. So that makes this ice less dense than the liquid water. The solid water less dense than the liquid water. Okay? So Demo's lesson, life lesson of the day, if you're at a party, because I know y'all are good boys and girls, and your ice sinks, probably not a lot of water in that cup. Probably a lot of other things that are less dense. Like from day one, something that was less dense. Ethyl alcohol, remember? Yeah? Way less dense than water. So water, ice, would sink if it's highly concentrated in that. So watch your ice. Make sure it floats. Okay? Demo's lesson of the day. Yeah, don't drink isopropyl. Yeah, don't do this at home. Demo's lesson is for protection, not for experimentation. All right. So let's move on to these. I know you've seen these before. We're going to run through these. I'm going to do the first 2 rows with you, and then you can ask me questions about the other rows. I should probably do the last 2 rows because those look a little bit harder to me. We're going to identify, first off, if it's a pure substance or a mixture. And what kind of mixture is it? Homogeneous or heterogeneous? You're going to tell me if there's compounds or pure, if there's compounds or elements in it, and also the state of matter. So let's just go ahead and start with I, and I want you all to holler out. I'll ask the question and you holler out. Pure substance or mixture? Pure. Element, compound, or both? Element. Solid, liquid, or gas? Liquid. Now, you can use your own system for writing things, what it is on there. All right, next one, J. Pure substance or mixture? Mixture. What type of mixture? Homogeneous or heterogeneous? I don't see a distinct phase there. I'm going to go with homo. Compounds, elements, or both? I'm going to argue both because what is this? It's a diatomic, which is really an element. People will argue, yeah, it's a molecule, but it's the same elements. Okay? To be a compound, technically, you have to have different elements attached. And then, so this is both. Solid, liquid, gas, what is it? Gas. Okay. I'm going to jump around. This one, P, is really important. Solid, liquid, well, let's go. Pure or mixture? Mixture. What type of mixture? Homo. So you should just write homo. Elements, compounds, or both? Elements. Those aren't attached, so they're all different elements, okay? Solid, liquid, or gas? Solid. So what is this an example of? Bronze or whatever, okay? Any sort of metal mixture. That's a solution. So don't let the word solution, you have to break your train of thought growing up. A solution, you think liquid. I know I do. But you can have solution being gas or solution being solid. O is interesting. Pure or a mixture? Pure. It's totally pure. Element, compound, or both? Compound. What phase or multiple phases? Gas and solid. How did this happen, solid to gas? Could be dry ice. What's the substance of dry ice? Carbon. Could that be carbon dioxide looking at this structure? Technically, carbon dioxide is not bent in shape, but I'll agree that it has one C in the middle and then two O's, so it could be carbon dioxide. And then what's that process of going to solid to gas called? Sublimation. Okay. All right. Y'all pick one out that looks scary. A? Really? Okay. I got some smart butts. K? We'll do K and N. I like L a little bit, and then we'll stop and we'll move on. All right, so K. Mixture or pure? Mixture. What kind of mixture? Hetero. No, it's not. It's homo. 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 Compound, element, or both? Both. And the state of matter? Gas. Exactly. L is interesting. L is what y'all have been wanting to say. What's L? It's a mixture. What kind of mixture? That's hetero. Do you see how there's like this distinct layer? What's hard about drawing this is when you draw layers, students tend to draw them where it's going to look like a solid because you want to draw a line and a line. Make sure if you're drawing a heterogeneous liquid, they kind of look like they're flowing, but they're still separated. Okay? So this is heterogeneous. Elements, compounds, or both? Elements, and is it solid, liquid, or gas? Liquid. All right, and then N, that's pretty, what is it? What kind of mixture? I'm going to go homo. Solid, elements, compounds, or both? Elements. And the phase? Yes. Okay. Up here, the phases, we have a gas and a what? Liquid. This irritates me. It's like a triatomic, whatever. It's like trilithium on Star Trek. I know that's the only thing I ever heard on Star Trek that I was like, that perked my interest because it was a formula. Anyway, yeah, that's not going to really, anything we really can relate that to other than the fact that it's three of the same. So technically it's an element. Okay? All right. Now that we know all about these pictures and these mixtures, we need to talk about some other new things that are going to be a year-long focus in this class. We really need to pay attention to laboratory equipment, laboratory technique. It is a big thing now where you guys are going to be writing a lot of your own lab procedures. And in doing so, you're going to be forced to pay attention to equipment, names of equipment, things you've pretty much taken for granted up to this point. So I'm going to be annoying, and I'm going to be like, what's that called that you have in your hand? What do you use that for? How do you put that together? I'm going to be putting you in the hot seat about stuff like that. So specifically what we're going to look at today are ways to separate mixtures. What makes mixtures different than pure substances is we can separate them with pretty simple physical means for the most part. And these are some of the ways we can separate these mixtures. So the first one is pretty much the most rudimentary thing in the world, the way to separate, and that's through decantation. In decantation, all you do is you pour off one phase from another. So obviously not going to be very good for many things. What type of mixtures do you think decantation is going to be best for? Hetero, exactly. So give me an example of what we could use this for. Sand and water, or rocks and water, or you could do oil and water. You know, if you pour off just the right layer, okay? But what's a drawback to this very caveman-like method? Christopher's like, you can't separate all of it. You know, if you have rocks and water, there's going to be some water left in there, okay? So this is for basic, simple separation. You guys did decantation when you did qualitative analysis last year at the end of the year, when you'd centrifuge your test tubes and you'd pour off the filtrate on top, right? The stuff you pour off is called the filtrate. And you'd sometimes use the filtrate, sometimes you'd use the precipitate. But do you remember if you had the precipitate left, didn't you have to put in water, stir it, what were you doing there? You were cleaning it by getting the rest of the filtrate off of that precipitate. So anytime you decant, you have to pay attention to that kind of thing. What are these vessels called here? Yeah, I know. I know it's stupid, but I want to make sure you guys understand all about the equipment. Like in Breaking Bad, of course, everyone wants me to make meth. I know. And about 2 years ago when Breaking Bad came out, 8th period had the plan. We were going to call it Shat Meth. Now, of course, for those of you at home, I'm not actually going to do this. It was fun, a fun little pretend project. They had the logo, they had the name, they had the selling, the whole thing set up. We were ready to roll. So anyway, never happened, as you can imagine. Next is filtration. In filtration, the most important piece of equipment is this triangular thing with the thing on the bottom. What is this triangle called? A funnel. A funnel. And in the funnel, we will put a piece of what? Filter. I said coffee filter. Yes, it's not coffee paper. It is filter paper. But yes, the concept of filtration happens in your coffee makers. I agree. you had the piece of round paper, what would you do? You folded it, remember, in quarters, and then you'd spread it apart and put it in the funnel. Okay, I know you did some funneling, some filtration in pre-AP. So with this, you get a better separation than in decantation. What type of solutions would this be good for? Hetero. Could I use it for homo, like sugar water or food coloring in water? No. What's the problem? They're dissolved. Those molecules are dissolved in pretty much the same size of the water, so they're going to come right through. So we need something a little more advanced for homogeneous mixtures, which we're going to talk about in a minute. But just to continue with this, we're filtering into this beaker. What's this thing that you always see in the lab and you use, and you might not know the name of, but you should? Oh, Lord. No, this thing. That's a beaker. This thing. Nope. Test tube holder is one of those little things that look like clampy scissors that you held your stuff in the flames, you know, your test tubes in the flames. It's a stand, okay, close. It is specifically called a ring stand. Originally, these were made where you had the ability to put on and off these rings, iron rings, where you could put stuff on like a wire gauze and then put something on it to heat underneath. In addition to putting rings on here, though, you can put clamps. That's a clamp. So it's clamped on, and you got this little thing that you can hold the thing, you know. So all of this stuff is removable, and you move it up and down and can adjust the height and all that stuff. All right, so you got to know the ring stand. So anyway, any questions on filtration? All right, our next process of separation is called evaporation. This beautiful little, very, very, very pricey piece of equipment, which I will lose it if you break these, are called evaporating dishes. Very original, considering you evaporate out of them. Evaporating dishes are just a lot of surface area, so evaporation takes place a little bit easier. You can put them in an oven, you can put them on a hot plate, or you can just set them out. You can put them under a Bunsen burner. All sorts of ways you can heat up an evaporating dish. It's made out of porcelain. That's why it costs so much money. It's probably a $3 sign piece of equipment. I kind of wish I could engrave dollar signs on all the equipment so you know. If you see a $4 sign piece, you better watch yourself versus a $1 sign piece of equipment. Anyway, I might start that system somehow. Evaporation is used to separate. What type of mixtures can we separate with evaporation? Homo and hetero, right? You could take salt water, put it in this, heat it up. What would happen? Water leaves, salt stays behind, okay? Still a pretty rudimentary way to do things, but it works. What about, can I do this with hetero? You said so, yeah? If I were to put sand in water, I could do the same thing, all right? So this is for both types of mixtures. There is a drawback to this, though, as far as separating goes. I can heat it up to make it, the question, someone said, Mike said it takes a long, is that Michael? I can't say Mike. Okay, because it's faster. It's one syllable as opposed to two, so it makes my life easier. Just kidding. So Michael was saying that it takes a long time. Typical, traditional evaporation where it's just sitting out does, but we can heat these and make it evaporate quickly, so that's really not a drawback. Caroline got it. You lose what you're evaporating. Half your mixture is gone. It's like, where did it go? Okay, so that is the big drawback to evaporation. So what people came up with to make it more useful is the concept of distillation. I know the first thing you think of when you hear distillation is moonshine. Okay, yeah, you can distill and get moonshine, but this is just evaporation on steroids. This is evaporating and capturing both portions of your solution. So I always tell my Department of Health story. When I first graduated, I took a job at the Department of Health as an analytical chemist. And we did all these rotations through all the different departments to get to know the place and all this kind of stuff. So for a while, I was in the food section. And part of that job was to work under FDA standards and verify labels on different foods, colors, dyes, things like that in candy. This particular rotation, I was doing the percent of fat in meats. So you guys have seen on meats it says 98% fat-free, and you'll usually buy that one because it's healthier, but it's more expensive, all that kind of stuff. But if you want it to taste good, you get the 80% protein, 20% fat-free, you know, whatever. Anyway, so those labels have to be verified, because if they weren't, anybody could have fatty meat and say it wasn't fatty. So that was part of my job. The first part of the distillation of the process of determining the percent of fat was the distillation. And I'm going to explain to you exactly what I did, and you'll learn about distillation in the process. First thing I did, which was gross, I took the meat, and it was usually ground meat that hadn't even been refrigerated for a couple days. So it was gross. Yeah. And you put it in a meat grinder, and you put it in the meat grinder over and over and over and over again until you made a paste. It was like toothpaste, but it was meat. It was pink toothpaste that was meat. It was really gross. So then, and it was fine when it didn't stink, but when it smelled, it was so bad. So then, I take my flask here. This is a Florence flask because it's got a round bottom, which is on the ring stand under a Bunsen burner, okay? And that flask, it had been pre-weighed, so I knew the weight of the flask. Then I put in meat. I could put in however much, as long as I knew how much I put in there. I put in about a gram of meat, okay? So I knew the weight of the flask, and I knew the weight of the flask after I put the meat in, and I could figure out how much meat exactly was in that flask. Start the heating process. Well, let me go back. I'm going to take a step back. I would put then sulfuric acid in there. It didn't matter how much sulfuric acid I put in there because it was all going to evaporate and go over to the other side. What that sulfuric acid did, what does sulfuric acid do to protein? Denatures it. You go from ternary to quaternary, you know, just takes all the structure, breaks it up. We get it down to the amino acid level because it's super, super concentrated. So literally, it dissolves everything in the meat except the fat, because the fat is a nonpolar substance and won't mix with that aqueous solution. So I start to heat it. The sulfuric acid slurry comes through here. And this is the difference. Evaporation, it would just go away into the atmosphere. This way, we recapture it through this condensation tube. Cold water from a faucet tube, and you can see we can hook up tubes if we wanted to those long things sticking down from the faucets. Cold water comes in and surrounds this inner glass tube that the steam goes through and recondenses it because it's cold. And then it drips into this flask. So my slurry here only contains the protein and the sulfuric acid. And if there are any binders in there at all, like whatever, that will be in there as well. There shouldn't be in pure beef. There should not be any binders. So then, what was left behind? Just the fat. So the flask, literally, there was nothing in it but a film all the way around it. Talk about a cleaning nightmare. I won't even get into how hard that was to clean. But then when I weighed it again, let's say the flask weighed 0.3, the difference between the weight and the initial weight and the last weight was 0.3 grams. What percent of fat was in my meat? 30%. So I could then say, hey, the label was right. They had to be, I can't remember, it's been so long, the exact amount. They could be plus or minus. I'd have to do multiple trials on one sample of meat, you know, to make sure. And I had like 8 of these distillation setups underneath this really humongous fume hood. So then that's all the distillation portion. But then I would actually take the slurry and I'd do a different set of experiments with a titration, which is another story for another day. And I could figure out my percent of protein. Ideally, what should those 2% add up to? 100. There was missing, something was going on. And they'd get reported, and then I'd be done. The thing about why I left being a chemist is because even though this kind of stuff was fun, it gets old really fast because you're doing the same thing every day, and I never really got to know what happened. Like, that sample was like 40% off, and I never knew if they put them in jail. Not really, but I never knew what happened. There was no follow-up. I was just like a machine chugging out data. It's not like on TV where you get to go to the crime scene, collect, run back to the lab, put your lab coat on, and test. It doesn't work that way. So yeah, I loved it for the first year, but then by year 3, I was like, I'm not learning anything new. I think I'll be a teacher. So see, you get to learn chemistry and hear my life story all in one time. It's awesome. All right, so distillation. Now that you know how it works, what is this good for? What types of mixtures? Hetero? Homo? Both. Okay? All right. Paper chromatography, really little simple one. You guys actually did this in pre-AP, and I'm pretty sure, did you? Anyone in Level Chem do this? Did they do anything with this? I'll need to ask. But anyway, what this is based on is the separation of a mixture. So this would be an example of maybe, I think did y'all do Kool-Aid? Yeah. So you had a Kool-Aid dot there, and you were separating the different dyes in that mixture. Okay? It's based, what makes this work, eluent, I don't know how to spell it, eluent. It's based on something called an eluent. The eluent is a substance that comes up. You have to choose an eluent that little dot will dissolve in, meaning it's attracted to it. Okay? Because as the eluent naturally is absorbed up the paper, if the dot is not attracted to it or dissolves in it, the dot won't move. The eluent will just go around it. We need to find an eluent. So if this is a polar solution, I'm sorry, if the solution, our mixture is polar, we want a polar eluent. Okay? And so as time progresses, the colors separate and you get these different values called our RF values you can determine to help identify the dyes. Right? Y'all remember that? So that's paper chromatography. And the bell's about to ring. The last one is called column chromatography, very advanced. I don't know if any of y'all have been in a biochemistry laboratory or in any lab where you've seen really, really tall columns in freezers, but you can put a protein mix in here and you can separate things by size, where fat stuff stays on top, little stuff comes out faster, and they come out at different rates. Okay, big proteins, little proteins. Or you can have things separate by charge called charge exclusion, where if all this medium here is positively charged, stuff you put in that's negative would stay because it's attracted to it. Stuff that's positive would shoot out because it's oppositely charged. You are not going to be tested on this. Just know we're going to do this at the end of the year, and it is a method for separating homogeneous mixtures, very, very complex mixtures of things. I forgot to tell you that. What is this? Homo. Yeah, you couldn't separate sand and water with that. That'd be tough, that sand crawling up the paper. All right, so do y'all have any questions on any of the separation techniques? All right, we'll see you guys tomorrow. Don't forget to do your homework, bring money for lab books, and sign up for UT homework as well.